Hello. In this video, I'm going to explore the question, is the Earth flat? If you think this is a valid question, and you think the answer is yes, then this video is not for you. This video is aimed at people who, for some reason, have started to think that this may be a valid question, and are wondering what to do about it. Before we do that, there are a couple of things that need to be addressed. Firstly, we're going to transform our question into a statement, specifically a scientific proposition. Doing that, we get the statement, the Earth is flat, to which we can assign a value of either true or not true. In mathematics, such a value would be considered like a switch, that is either on or off. However, this is not a mathematical proposition, it is a scientific proposition, and in that case we would be better thinking of the assignment of a value as a slider which starts at not true. The way the slider moves is by applying the scientific method. In general terms, that is, an experiment is performed and then undergoes a process of peer review, which involves direct critique of the experiment by a recognised peer group, direct repetition of the experiment, and then maybe repetition of the experiment under other relevant circumstances, as a way of accumulating evidence that the community agrees moves the slider to the left. So, if we want to establish the truth value of the scientific proposition the Earth is flat, we need to engage in the scientific method in a way that can provide the evidence necessary to move the slider to the left. Before we look into how we might use this process to investigate our flat Earth proposition, I want to address some other ways that claim to be trying to reach the same goal. The first is a claim that the Earth is not spherical. Let's first render this as a scientific proposition so it becomes the Earth is spherical, which by scientific consensus has the slider hard over to the left. Those who are following this not spherical strategy are aiming to cause the slider to move back towards the right by undertaking experiments that falsify the proposition in some way and to some extent. However, the proposition that we are really interested in is the flat Earth one, which is completely separate. Falsifying the spherical Earth proposition does not of necessity have an impact on our flat Earth proposition. The best that we can hope for with this approach is that the parts of the spherical Earth's experiment might have relevance to the flat Earth proposition, but even then they must still be put through the scientific method, where a positive result may cause a movement of the slider to the left. This approach isn't really tackling the notion of a flat Earth. Another approach you will encounter is an appeal to direct observation, which we'll call the "it looks flat to me" assertion. One version of this is "I don't see the curve," which in reality is a version of the not spherical approach. Otherwise, this approach makes claims about what an observer can see at a particular place at a particular time, and claiming that this is only possible if the Earth is flat. This may use captured images as the form of evidence. However, the scientific method is rarely applied to this approach. What does it mean to repeat such an observation? How do we compare similar observations from different places or at different times in order to acquire the necessary evidence to move the slider to the left? That being said, I suggest that the whole direct observation approach is fraught with other problems, mostly due to the way the human visual system operates, and which I'm going to try and demonstrate. In a moment, two horizontal lines will appear on screen, and I would like you to identify which of them is longer. If your visual system operates within normal parameters, you should quickly realise that the lines are actually the same length. But what about these two lines? If you haven't encountered this setup before, you might judge the lower line to be longer. However, if we take a measuring instrument to the two objects, we see that the horizontal lines are the same length. Our visual system has been fooled by the context in which the lines exist. But that's not all. Here is a drawing of a Necker cube. If your visual system operates within normal parameters, then you are probably experiencing this as 3D cubes. Not only that, some of you may see the black faces pointing down to the left, while others see the black faces pointing up and to the right. You may even experience a switching between the two. This is an illusion, of course, but this can be so strong that if I ask if you can see the hexagonal shapes, you may even deny that there are any in the drawing. Yet here is one of them. Similarly with diamond shapes. In fact, the whole drawing is a tessellation of this diamond shape, and there is not a single square or cube in the entire drawing. Only by deploying a measuring instrument will we be able to clearly see these facts. So, how should we proceed in investigating the flat Earth proposition? We need to take some measurements from reality and use them to explore the notion of a flat Earth, such that we can gather evidence to move the slider to the left. But what should we measure? We want something to which we can apply the scientific method, which means something that can easily be subjected to peer review. To this end, I am proposing taking measurements of the position of the Sun. For this particular set of experiments, we're going to take two measurements. The direction we need to face to look in the direction of the Sun, called the azimuth angle, and the angle we need to tilt our head up, relative to an agreed reference, called the elevation. Of course, looking at the Sun without appropriate precautions is extremely dangerous. Instead, we are going to extract data from the Suncalc website with the proviso that we can always validate that information by going and taking actual measurements of the Sun. Suncalc allows us to enter a place for which we wish to obtain measurements. We also need to input a date, and in these experiments we will be using data supplied by Suncalc, namely solstices and equinoxes. For the time, we are going to use the culmination time provided by Suncalc. This is the time that the Sun is at its highest point on that day, also known as solar noon. Note that the culmination time is given to the nearest second, while the time can only be set to the nearest minute, which means there will be a small error in the data. We may need at some point to determine whether that error is significant to the outcome, but for the moment we will assume it is not. Once these values are input, we can read the elevation, here called altitude, and azimuth directly from Suncalc. Later on, we will also make use of some of the geodata Suncalc provides about the location that's been selected. We're going to start by selecting Daventry in the UK as the place from which we're going to extract our data. We're going to use the upcoming winter solstice, spring equinox and summer solstice so we can validate these with actual readings should we so desire. Inputting these values and the culmination time into Suncalc, we find that the azimuth reading for all three dates is 180 degrees. Therefore, only the elevation is different on each of these dates, and that is what's shown in this table. Some questions now arise. Firstly, why does the elevation change at all throughout the year? What are the mechanisms that are responsible for this? At some point, we would need to address these questions in the exploration of the flat Earth proposition. More immediate is to explore how this data we've collected interacts with the notion of flat Earth, and to do that we consider the question, what if the Earth is flat? We start with the data. Because the azimuth value for all three readings is the same, we can use a ruler, protractor and some squared paper to visualize the relationship between each measurement, as shown. With this visualization of the data, we will enter our what-if world and speculate on how this data would interact with notions we think should be true of a flat Earth. We start with the idea that the local horizon we use to measure the elevation is a small segment of a much longer line from which other observers will also be measuring the position of the Sun. We'll call this the extended horizon to emphasize that this is an extrapolation from an actual piece of data. Of course, we know that the existence of hills and valleys mean that this might not be exactly true, but for the moment we will assume that such differences are not significant to the analysis. Later on we might have to adjust or justify that assumption. Somewhere along the extended horizon there should be a point where the Sun is directly overhead. That is, an elevation of 90 degrees. We don't know exactly where. However, since such an elevation makes a right-angled triangle with the observer and the extended horizon, we know that wherever we place it, this will give a scale model of the relationship between these three things. So we choose to place the observer here. The 90-degree elevation will thus intersect the December Daventry observation here, which gives us the position of the Sun in this scale model. If we knew the distance from Daventry to this observer, we could then calculate, through trigonometry, the distance to the Sun from each observer. However, we would then need to find a way to make a direct measurement of that distance as a step to validating the extended horizon hypothesis. Instead, let's introduce a new hypothesis into our what-if world. A common claim is that the movement of the Sun in a flat Earth world moves about a plane that is parallel to the extended horizon. So let's draw that onto our diagram. Having done that, we have now predicted an actual position for the Sun in March and June, being the place where the Sun plane and the elevation lines intersect. In March, the Sun is here, and from that we can infer that the 90-degree observer will be here. Similarly for June. Now we have generated some new values that we can measure along the extended horizon. That is, the distance to the 90-degree observers on each of those dates. One thing to note is that the relative distance between our hypothetical 90-degree observers, that the distance from March to June, is much less than from December to March. If this turned out to be true, we might have the basis for moving the truth slider to the left. Stepping out of the what-if world for a second though, 90-degree observations on the dates and times chosen take place on the equator and the two tropics, and these are known to be about the same distance in the two cases we mentioned, while inside our what-if world there is a substantial difference in the two measurements. Our analysis has also given a predicted position of the Sun relative to Daventry on each date. If we take a ruler and measure the distance on our diagram, we see that the distance to the Sun in December is more than 3 times the distance to the Sun in June. If the Sun remains the same physical size throughout the measurement period, then we would expect to be able to easily measure the apparent size difference. Consider putting 2 5-pence pieces onto a ruler, one at 1 foot and one at 3 foot. If we look down the ruler, we can clearly see a major difference in the apparent size of the 5-pence pieces. If such an attribute were true for the Sun, we might expect to see that reflected in popular culture. While it's probably easy to find references to the Sun being low in the sky during winter, I'm not aware of any references to the Sun being small in the sky during that period. This should make us wonder about the results we are getting from our analysis. So, what should we do next? We could take the predictions made with this analysis and see if they are found in reality. However, there are several issues we need to consider before we expend time and effort on such an endeavour. If the idea that the 90-degree observers are at the equator or the tropic lines, then should we proceed with that investigation? What about the predictions about the apparent size of the Sun at each date? And we should note that these predictions are all piled on top of the idea of the extended horizon. So rather than setting out on an expedition to try and validate the predictions, it might be wise to try and get a better, more precise notion of the extended horizon. How should we go about that? Well, we want to try and ensure that all observers are really measuring off the same extended horizon. We might also like to try and minimise the effects hills and valleys might have on any measurement or predictions we might make. To that end, we're going to deploy something else that is often asserted to be true in flat Earth theories. That is, that water always finds its level. From this, the claim is that all observers next to a body of water are part of the same extended horizon. So our what-if world now has this as its initial hypothesis, and we need to collect some data that will help explore this notion. We're going to use the following criteria for our next set of measurements: that the observations are taken at solar noon on the same date as before, and that the places we make those observations are all next to the same body of water. The places we have selected are Plymouth in the UK, Malaga in Spain, and Abidjan in Côte d'Ivoire, which are all next to the Atlantic Ocean or seas connected freely to the Atlantic. As before, we extract the measurements from Suncalc. As well as the elevation data, we have also extracted the relevant geodata, which show that the height difference above sea level is only tens of metres, while they are all 4 degrees west of the Greenwich meridian to within a few minutes. Again, we may have to consider in the future whether these differences are going to have impact on our analysis, but for the moment we'll assume that they don't. Note that for the December reading in Abidjan, the azimuth value is given as 360 degrees, so we will have to make an adjustment to the elevation value when we use it. To start the analysis, we'll draw a horizontal line representing the extended horizon constructed from the water level hypothesis. We select two of the places from our dataset. In this case, we'll choose Plymouth and Abidjan and position them on this line. Basic notions of triangulation then allow us to construct a scale drawing of the relationship between the two places and the Sun, as shown here. The first thing to notice is that our earlier notion that the Sun remains in the same plane throughout the year cannot be true in this flat Earth world. Note that from Plymouth, the apparent size of the Sun is not greatly different for each date. However, from Abidjan, we encounter the same apparent size issue as with our Daventry analysis, and to the same degree. How should we use the data from Malaga? Somehow we need to find a position from Malaga along the extended horizon. To do that, we are going to use a simple truth from geometry, that if you draw a straight line between two parallel lines, this angle here is the same as this angle here. This will allow us to triangulate back from the position calculated for the Sun to locate Malaga on the extended horizon, like this. Having located Malaga on the extended horizon using the December data, we can now add observations made on the other dates. However, this creates a big problem in the analysis. If we add in the March observation, we find that it does not line up with the position of the Sun calculated from the other two places. Similarly with the June data. How are we to interpret this? Our assumption was that all observers were taking measurements of the same object, yet this calls that assumption into question. If different observers are measuring the position of different suns, then this whole analysis falls apart. Instead, let's insist that there is only one Sun, and instead triangulate the position of Malaga on the extended horizon from the Sun positions for each date, like this. Now we are faced with a different problem. Where is Malaga? If our extended horizon hypothesis is true under this analysis, then the distance from Abidjan to Malaga must be different on each of the days that we take measurements. In examining some of these plots of the data, something interesting can be seen. Going back to the first sea level plot, let me draw our attention to the Abidjan measurements. The way the data is presented on the page makes it look like the angles between December and March and June are quite similar in size. If we take a protractor to the drawing, we find that the first has an angle of 23 degrees. Interestingly, so does the second. If we make similar measurements for the other places, we find that all such angles are 23 degrees. What are we to make of this? If we return to the data themselves and calculate the angles directly, we find that while not precisely the same, there is also very little difference in the Plymouth measurements. Similarly for the other two places. In fact, we can render these relationships as being around 23.4 degrees plus or minus 0.08 of a degree. We also find that this is true when we analyse the data we captured for Daventry, which poses the question, if we take these measurements in other places, will we find the same relationship? If we are taking these measurements of the same Sun, what does this mean for the reference from which we measure the elevation? If these internal angles are the same in each case, then the major difference between the three datasets is in the initial angle between the local horizon and the December elevation. How then can we construct a single extended horizon from which all elevation measurements are made? This issue can easily be seen in this diagram. Start by plotting the Plymouth elevation measurements from a horizontal line, and then use a protractor to measure back to find the horizon line for Malaga and Abidjan. If all measurements of elevations are of the same Sun, then the local horizon lines used to make those measurements are at very different angles to each other. Let's draw some conclusions from our analyses. Firstly, the notion of extended horizon isn't able to correlate the elevation measurements that we made even when we tried to make that notion more concrete by using sea level. In fact, using sea level invalidated the earlier notion that the sun moved about on the same plane throughout the year. Also, it is not consistent with the idea that there is just one sun being observed. If we insist that there is just one sun, then we find that Malaga must be in a different position between Plymouth and Abidjan on each of the measurement dates. The extended horizon notion hasn't generated any evidence that can be used to move the slider to the left, and our what-if world is empty of hypotheses. We need to construct new notions, very different to the ones we have been exploring, to make the measurements we've taken be consistent with the idea of a flat Earth. And therefore, our scientific proposition that the Earth is flat has its value stuck at not true. Thank you for watching. Feel free to make observations, questions and corrections in the comments box.